Ever stop to wonder how that incredibly sleek smartphone in your hand can run so many apps at once?
Or, how AI models just keep getting smarter.
Exactly. Or self-driving cars, navigating cities.
Yeah.
It feels like magic, right? Engineers are somehow packing more power into tinier spaces. It's brilliant.
It absolutely feels like magic, but behind it all, there's this invisible architecture, an unsung hero making it all possible.
And that's our topic today, isn't it?
That's right, advanced packaging. And this isn't your grandpa's chip packaging, not just putting a chip in a box.
No, it sounds way more complex, like a microscopic city inside our tech.
Precisely, an intricate city where everything connects and works together at speeds we only dreamed of before.
Okay, so let's dive in. We're looking at recent advances and trends in advanced packaging, right? By John H. Lau.
Yep, published in iTransactions on Components, Packaging, and Manufacturing Technology, January 2022. That's a pretty significant paper in the field.
It's a top-tier journal, definitely. So our mission today, unpack advanced packaging. What is it? Why is it suddenly so critical? And what are the mind-blowing innovations happening?
Let's do it.
So, okay, first question. Why is advanced packaging such a big deal all of a sudden? I mean, beyond just the tech insiders, why should you, listening now, care?
Great question, because honestly, it's impacting your daily life constantly, even if you don't see it.
How so?
Well, there are basically 5 huge growth engines pushing this forward. First, mobile devices. Think smartphones, smartwatches, fitness trackers, all getting smaller, more powerful.
Right, obvious one.
Second, high-performance computing, or HPC. This powers, massive supercomputers solving global problems, designing drugs.
The really heavy lifting stuff.
Exactly. Third, autonomous vehicles. Self-driving cars need insane processing power instantly. Reliability is key.
Makes sense. Number 4.
The Internet of Things, or IoT, smart factories, smart homes, health monitors, intelligence everywhere. And finally, big data, cloud computing, edge computing, processing data closer to where it's made. All these things demand more from the chips, and therefore the packaging.
And I guess AI and 5G are just pouring fuel on that fire.
Oh, absolutely. They're like twin turbochargers.
Right.
AI needs immense processing for all that data.
Learning, recognizing patterns.
Yeah. And 5G needs incredible speed, super low latency for real-time stuff, connected cars, talking to each other, instant cloud gaming.
So these two, AI and 5G, they create specific challenges for packaging.
Definitely. We need faster speeds, way higher interconnect density, packing more connections into tiny spaces and smaller connection points, the pad pitch.
And chips are getting bigger too, right?
Yeah.
That must generate heat.
A lot more heat. So managing power dissipation is huge. It's like, imagine building a super fast data center, multi-story, inside a matchbox.
Wow.
And each new version has to be even faster and more efficient. It's a massive puzzle, but also a huge opportunity for packaging innovation.
Okay, tiny, powerful cities. So how do these microscopic brain cells, the chips, actually, talk to each other? The connections must be unimaginably small.
They really are. So the basic method is called flip chip bumping.
Flip chip bumping. Yeah.
The traditional way is C4, controlled collapse chip connection, uses little solder bumps, most common for a long time.
Right.
But for the really high density stuff, where connections are super close, we use C2 microbumps.
C2. What's different?
They're not just solder, they're actually a tiny copper pillar with a solder cap on top.
Oh, copper. Better conductor.
Exactly. Better thermal and electrical performance than the old C4 bumps. Lets you pack things much tighter, get heat out better.
Okay, that makes sense. But then I've heard this term hybrid bonding. That sounds even crazier. Like bumpless. How does that work?
Yeah, bumpless is a good way to put it. Hybrid bonding, or DBI, direct bond interconnect. It basically eliminates the separate bumps.
Wow.
It's pretty ingenious, actually. It combines a dielectric bond that's like the insulator with a direct metal bond. Came out of places like RTI and Ziptronic, which Xperi bought later.
Okay, so how do they do it? Sounds tricky.
It's incredibly precise, like microscopic surgery. First, you need surfaces that are perfectly flat and smooth. They use something called CMP, chemical mechanical polishing.
You're polishing a mirror.
Exactly like that. Super smooth, with the metal bits slightly recessed. Then they use plasma to activate the surfaces. And then at room temperature, you just press the dielectric parts together and boom, they bond instantly. Oxide to oxide bond.
Just like that.
Just like that. Then you apply some heat, annealing, maybe 150 to 300 Celsius. The metal, like copper, expands slightly and fuses directly copper to copper.
Wow.
Big pluses. Minimizes copper oxidation, creates a hermetic seal, protects the connection.
That is seriously next level. So are we seeing this in actual products yet?
Oh, yeah. Sony was an early adopter. They used copper-to-copper DBI in their image sensor, the IMX260.
Image sensor, like in a camera.
Exactly. It was in the Samsung Galaxy S7 back in 2016. Helps make the sensor smaller and better by getting rid of older connection types like TSVs for that part.
Okay, so it's been around a little while in some areas.
Yep. And TSMC uses it in their Soicus technology system on integrated chips. They get almost zero insertion loss, super fine pitch, super high density.
And Intel.
Intel's pushing it hard with Foveros Direct. They're talking like 10,000 bumpless connections per square millimeter. At a 10-micron pitch, it's tiny.
That's insane density, the train car analogy you used, fusing them together instead of coupling them.
That's pretty much it. Smoother, faster, more integrated, a total shift.
Okay, that visual helps a lot. Seamless integration. So zooming out, there's this classification system, right? Like a ladder, 2D up to 3D, based on density and performance.
Yeah, it's a good way to think about how things are evolving. Each step up adds more complexity, more capability.
So let's walk up the ladder. Start with 2D.
Right. 2D IC integration, that's the most common today. Multiple chips side by side on one substrate. Think of a single-story ranch house, all rooms or chips on one level.
Like system and package, SIPI, and phones and watches.
Exactly. Very common for consumer stuff. Lots of functions packed in.
Okay, next run. 2.1D.
2.1D IC integration builds on 2D. You add thin film layers on the substrate or embed tiny silicon bridges. Intel's Enum IB is an example. Chips talk horizontally across these bridges.
So like adding another floor, or connecting two houses with a sky bridge.
Good analogy. Adds more complex paths. But manufacturing yield can be a challenge here, getting those layers right.
Gotcha. Then 2.3D.
2.3D IC integration. Here, you make a separate high-density interposer substrate and the main package substrate separately, then connect them.
Like building specialized floors offsite for a skyscraper?
Kind of, yeah. That interposer gives you much denser wiring than you could get directly on the main substrate. Higher performance than 2.1D. Cisco uses this for some big network chips, connecting ASICs and high bandwidth memory.
Okay, getting complex. What's 2.5D?
2.5D IC integration. Now we're talking really high performance. Chips sit on a passive silicon interposer that has through silicon vias, or TSVs.
TSVs, those are the vertical connections through the silicon.
Exactly. So this interposer is like a dedicated, super complex utility floor in a skyscraper, handling all the high-speed data and power, connecting the chips above it. Then that whole assembly goes on the main package substrate.
Used for HPC, right? High-performance computing.
Absolutely. Think powerful GPUs. AMD's Radeon R9 Fury X from 2015, NVIDIA's Pascal 100 GPU from 2016. They both used high-bandwidth memory, HBM, sitting on these TSV interposers.
And HBM itself uses stacking, doesn't it?
It does. HBM stacks DRAM chips vertically using TSVs and microbumps to connect them. Gets massive memory bandwidth right next to the processor.
Okay, so that brings us to the top, 3D.
3D IC integration, the pinnacle. Chips stacked vertically and connected directly using those TSVs going straight through the active silicon.
The ultimate skyscraper, super fast elevators between floors.
That's the idea. Hyper efficient. But, quick distinction, that's different from 3D IC packaging, which also stacks chips but might use older connections like wire bonds or flip chips between the layers, not direct TSVs through the active chips.
Get it. And you mentioned HBM again. HBM, HBM2, soon HBM3. That's crucial for AI and 5G stuff.
Absolutely essential. You need that massive bandwidth, and HBM delivers it with lower power than traditional memory setups thanks to that stacking in close proximity.
Okay, so we've got these incredible ways to connect and stack chips, but is there a limit? Does trying to build one single giant superchip just get too hard or expensive?
You've nailed it. That's a huge issue, challenging Moore's law itself. The cost is just skyrocketing.
How much are we talking?
Designing a cutting-edge 5-nanometer chip could be over $500 million. Just design. Then maybe another $1 billion for developing the manufacturing process to get decent yields.
$1 billion for yield. Wow.
Yeah. And the yield problem itself is killer for big chips. A large monolithic chip, one single piece of silicon, if there's one tiny defect anywhere, the whole thing is junk.
Ouch.
You might get, say, only 15% good chips from a wafer if the chip is really big, like 360 square millimeters, but break that into 4 smaller 99 square millimeter chiplets. Combine those. Your yield might jump to 37% or more.
Okay, the economics are screaming, don't build giant chips.
Preem.
So if the giant chip is too hard, what's the alternative? Like Legos. building with smaller blocks instead of carving a statue.
Exactly. Fantastic analogy. The solution is chiplet design and heterogeneous integration packaging.
Chiplets. Okay.
Think of building a custom car. Instead of one giant factory trying to make everything, you get specialized, optimized parts, the chiplets from expert suppliers. Maybe one makes the engine, another the transmission.
And then you assemble them expertly.
Right. Each chiplet is a functional block, often reusable IP, optimized for its job. Maybe one uses the absolute latest process tech, another uses something older and cheaper where it makes sense.
And the advantages are better yield, obviously.
Significantly better yield, so lower cost, faster time to market because you're reusing proven designs, reduced design costs overall, better thermals too because you spread the heat out.
And modularity, easier to upgrade or mix and match.
Huge advantage, much more flexibility.
Okay, this sounds like a revolution. Where's this chiplet approach happening now in the real world?
Oh, it's definitely happening. Ulinx was an early pioneer back in 2013. They broke a big, low-yield FPGA into 4 smaller chiplets. TSMC packaged it for them using their CoWoS stack.
CoWoS, chip on wafer on substrate, that 2.5D thing.
That's the one. Then AMD, mid-2019, their EPYC server chips, up to 64 cores,
Yeah.
9 chiplets. They cleverly put the CPU cores on cutting-edge 7-nanometer silicon from TSMC because cores need the best. But the I/O memory controllers, they put those on older, cheaper 14-nanometer silicon from Global Foundries. Smart economics.
It's very clever. Mix and match processes.
Yep. And AMD's even stacking chiplets now with their 3D V-cache, adding extra cache memory right on top of the processor chiplet for faster gaming. Around 15% faster, they say.
Cool. What about Intel?
Intel shipped Lakefield mobile processors in July 2020 using their Foveros 3D stacking. That was the first high-volume 3D integrated processor for mobile. They split the CPU, GPU memory into chiplets and stacked them face-to-face on an active interposer.
Active interposer. So the interposer itself has logic.
Potentially, yes. And looking ahead, Intel's Ponte Vecchio GPU, they're calling it a spaceship of a GPU, like 47 different chiplets, different processes, different architectures, maybe even from different factories, all integrated.
47 chiplets. Wow.
And TSMC isn't standing still. August 2020, they announced their 3D Fabric technology, a whole ecosystem for designing and integrating chiplets for everything mobile, HPC, automotive, IoT, high volume expected in 2022. It's really taking off.
Okay, so chiplets are a massive trend. Beyond stacking and splitting, though, are there other specialized packaging tricks making things better? Especially for, say, tough environments, cars, factories.
Good point. Yeah, let's talk fan and packaging for a sec. Specifically, the 6-side molded WLCSP.
Wafer-level chip scale package, 6 sides molded.
Right. They mold the front, the back, and all 4 sidewalls. Makes it incredibly tough. Super reliable.
Where would you need that?
Think automotive electronics. 8-die systems, advanced driver assistance systems. Stuff that absolutely cannot fail. Vibration, temperature swings.
Makes sense. How much tougher is it?
Significantly, tests show its characteristic life in thermal cycling is nearly 3 times longer than a standard WLCSP, like 100 and 137 cycles versus 368. It's like putting the chip in a tiny vault.
Wow. Okay. And fan-out. You mentioned TSMC used that for iPhone.
Yeah, fan-out packaging really took off with TSMC's NFO integrated fan-out for Apple starting in 2016.
So how does fan-out work?
Basically, you use a temporary carrier, place the chip, and then build out connection layers, redistribution layers, or RDLs, beyond the chip's original footprint. Gives you more space for connections.
Spreading the connections out, kind of?
Exactly. There are a few ways to do it. Chip first, face down is simple, low cost, good for things like mini LED drivers, maybe some 5G antenna packages. Chip first, face up. Or RDL first, which is more complex but gives you the best density and performance.
Fascinating how much detail goes into just connecting things.
Mm-hmm.
But none of this works without the right materials.
Yeah.
Right? Especially with high speeds, heat. What's the material magic?
You're spot on. Materials are absolutely fundamental, especially the dielectric materials, the insulators. For high speed, high frequency, especially 5G, you need low decay and low decay.
DTK.
Decay is the dielectric constant. Permittivity, DF is the dissipation factor, loss tangent. Think of your data signal as a race car. The dielectric is the track. High DKDF is like a bumpy, sticky track. Slows the car down, wastes energy, loses signal. Low DKDF is a super smooth, non-stick track. Data races along efficiently, minimal loss.
Got it. Smooth track for fast data. What else?
They also need to have a low CTE coefficient of thermal expansion.
Why is that important?
It needs to match the CTE of the copper wiring inside it. When things heat up and cool down, which they do, constantly the insulator and the copper need to expand and contract at almost the same rate.
Ah, so they don't pull apart or stress each other out.
Exactly. If they don't match, you get stress, warping, tiny cracks, delamination, basically device failure.
Yeah.
Especially in these densely packed systems, that thermal compatibility is critical for long-term reliability. They have to be thermal soulmates.
Thermal soulmates. I
Wow.
like that. Wow. What an incredible journey through this hidden world. We went from tiny C2 bumps
To bumpless hybrid bonding
through all those 2D, 2.5D, 3D layers.
and landed on the chiplet revolution.
It really feels like we've peeled back a layer on how modern tech actually gets built.
It's been quite the deep dive, and the big takeaway, I think, is that advanced packaging, it's not just some niche thing anymore.
No, it sounds critical.
It is the critical enabler for the whole electronics industry. It's how we keep pushing technology forward, even as traditional chip scaling gets harder and more expensive.
So it's full of challenges, cost, complexity, finding those materials.
Huge challenges, but also incredible opportunities for innovation. It's shaping literally everything electronic in our future.
So for you listening,
Yeah.
what does this all mean? When you pick up your phone, get in car.
It means faster phones that don't melt in your hand, more reliable self-driving cars, processing data instantly, smart devices everywhere, seamlessly working, amazing AI understanding the world.
All powered by these hidden architectural marvels we just talked about.
Exactly, all unlocked piece by tiny piece by advanced packaging.
So next time you marvel at your gadget, remember the invisible, intricate ballet happening inside. And maybe wonder, what new capabilities will these microscopic cities unlock next?
What's coming next is going to be fascinating.